Good morning everyone, my name is Preetham and today I'm going to explain a very important topic of organic chemistry, but before that let's just go over a little bit of scenario. Let's say a man has gone to a doctor and he has complained about an eye rash. The doctor has examined the man and said, okay, it's just a mild rash and can be treated with a small medicine. The doctor has said the nurse to get an L isomer of a compound, okay, an L isomer of a compound. Now the nurse goes, she finds two chemicals, but she's confused, they look alike. She's confused, which is L, which is D. So she randomly brings out a compound, which turns out to be a D isomer of compound, something that the doctor did not want to treat the man with. And the doctor trusts the nurse and he treats the man with the D isomer and the treatment gets over. And after a few days, the man returns saying that he complains about slow vision loss. So the man who had a mild rash now complains with a vision loss. Now the doctor, who has actually done well in his 12th standard chemistry, understood this problem very quickly. And he told that this has got to do something with stereochemistry. So that is my topic for the day. It's called stereochemistry. Now stereochemistry is just like a big story of organic chemistry, which I would like to break down into smaller points for you all. So let's start off with the nature of this topic, which I would like to explain. First, let's go over basic terms. Let's just recall a few terms from organic chemistry, and then let's go through SN1 reactions, SN2 reactions, and then let's actually go to the stereochemical aspects in these nucleophilic reactions. Okay, let's head on to some basic terms. Optically active compounds. So these are the type of compounds that have a tendency to rotate a plane of polarized light that passes through them. To have a deeper knowledge about this, scientists have conducted an experiment which involves setup of an unpolarized light. This is something called as a Nicol prism. A Nicol prism is the prism that is used to convert unpolarized light into a plane of polarized light. And that is, they kept a compound, a slab, which has optically active compounds or chiral compounds in them, and which and finally something that we can see with. So when the bulb actually produces something called as unpolarized light, means the plane of polarized light, they can all be in different planes. So if one wavelength goes this way, another one goes this way, another can go this way. So all different planes. So what a Nicol prism does is it converts all those planes into a single plane, and then that passes through chiral compounds. And the chiral compounds actually produces two different wavelengths of light, where only one can be seen by humans because it is in the field of view of humans. So that is the experiment that was conducted by scientists. Moving on to the second term is chiral and achiral molecules. Okay. So chiral molecules are those type of molecules that have something called as a chiral center in them. So yeah, chiral. Okay. Yeah. So chiral centers are those centers of chiral compounds that have four different substances wrapped around it. So for example, we have this carbon, which is a center of this compound. This carbon has CH3, H, chlorine and an ethane molecule. These four are different compounds that are wrapped around this. So hence this is called as a chiral center. Now if you move to achiral molecules, those are the compounds which are an achiral center. For example, if you take this molecule, we have this as a carbon and we have these four substances. We see that these two are like substances. Means this carbon is not wrapped around four different but actually only two different substances. These are called as achiral compounds. So we can break those into chiral, achiral compounds. Chiral, which refers to chiral center, means it can have four different substances. Achiral means achiral centers refers to centers with not four but actually it contains a like substance around them. And we can actually speak about a few key terms called as superimposable and non-superimposable, which means that the best example is a pair of hands. Let's take a hand, let's have a plane of mirror passing like this. So if you put a hand here, we are going to obtain an image like this, right? Mirror is going like this. So if you actually take these two hands, we overlap them, we see that they are perfectly overlapping. These are called as superimposable images, meaning that they can be perfectly overlapped upon each other without any differences. But on the other hand, if you have a plane of mirror passing like this, we put a hand, we're placing like this, a mirror, we're going to obtain an image like this. Right? If you take these both hands, we place on each other, we see that these are not perfectly overlapping. We have two different things, we have thumbs coming outside. So these are not completely overlapping. These are called as non-superimposable images. Alright, moving to the next one. We have a few compounds called as enantiomers. Now enantiomers are the non-superimposable images of chiral compounds. So for example, as I explained, non-superimposable, those are a pair of hands like this, means they are not perfectly overlapping. So these are the non-superimposable mirror images of each other. So for example, we have these two images. We can see that this center and this center are chiral and they're exactly the same because they have four different substances. Now if we take a mirror image, we obtain this image. OH is on the right hand side primarily, but after taking mirror image, it has come on the left hand side. Means they are perfectly mirror images of each other. Now, if you take exactly this compound and put it on this side, we get OH on this side and H on this side, like this, which means that they are not superimposing on each other, just like a pair of hands. So these are called as non-superimposable images, and the mirror images of those two are called as enantiomers. Right. Next term is called as retention of configuration. Now, retention is the preservation of spatial configuration of molecules. Now, for example, we have this molecule. Let's take an OH molecule that is attached to this carbon, and a Cl nucleophile is going to attack this OH. Now, on the reaction getting happened, we have this chlorine attacking the OH, and the OH just leaves out as a leaving group. Now, we see that the CH2 is on this side and the H is on this side. Exactly after the product, we see the CH2 on this side and H is on this side, meaning that the product did not get inverted, it did not get flipped. We obtain exactly the same thing, but with just a different nucleophile. That is called as retention. Moving on, we have something called as inversion, the opposite of this, which means that we have a molecule where bromine is attached to this chiral center because it has 4 different substituents around it. Now, after the reaction, we have iodine attached to this nucleophile. We have a different nucleophile, obviously. But then we have here the hydrogen on the left hand side, but here we obtain on the right hand side. This is called as inversion of configuration, meaning we had a compound like this, but then after the reaction it got flipped, means hydrogen came this side, but then CH2 CH2 remain on this side. So the product got flipped. That is called as inversion of configuration. Okay. So moving to a basic of nucleophilic reactions, we have 2 types of nucleophilic reactions, namely SN1 and SN2. SN1 refers to nucleophilic substitution reaction unimolecular, and SN2 refers to nucleophilic substitution reactions bimolecular. So let's go in depth of each other. So let's start with SN1 reaction. So in SN1 reaction, it involves basically 2 steps. First step, so this is an alkyl halide. So the first step refers to the slow cleavage of the carbon and a halogen bond. Alright? And halogen here can be Cl, bromine, iodine, etc. So it refers to the slow cleavage of the carbon and the halide bond, which means this will give something called as a carbocation. Means this is deficient of an electron which the halogen previously had. And now this is the first step. The second step is the attack of nucleophile to complete this carbocation. Means previously there was a halogen. Now another nucleophile is coming to replace this halogen and to complete the valency of this carbon. That is the 2 steps of the SN1 reaction. Alright, we can see with this example. We have CSC, C and Br over here, but then after the first step, which is the cleavage of this carbon and halide bond, we see that there was a carbocation formed and the bromine has come outside. Right? In the second step, we have a nucleophile incoming, that is OH. OH is the nucleophile. When this attacks in this place, we have something called a C6CH2OH. Means in place of Br, we have now OH. So Br has gone out, and in that place, OH has come. Right? Yes. So we saw that in the first step, it involves the formation of a carbocation. And we all have learned that in 11th standard, the priority order of carbocation reactivity is 3 degrees is greater than 2 degrees is greater than 1 degree. We all know that this is the primary order of carbocation stability. Now the same order follows for SN1 as well, because SN1 involves the formation of carbocation, and since this is the order for carbocation, that will be also the order of SN1 reaction. So the priority order for SN1 reaction is 3 degree, then 2 degree, then 1 degree. Now moving on, you might be wondering, what is the stereochemical aspect now in SN1? We have gone through the basis of SN1. Now what is the stereochemical aspect? The stereochemical aspect is that when the carbocation is formed, we have something called as a trigonal planar structure. This is called as a trigonal planar structure or sp2 hybridized. We have done this all in 11th standard in chemical bonding. Right. So let's say a nucleophile is coming. It's going to attack this carbocation present over here. Now we see that these two are actually symmetric to each other, which means that let's say a nucleophile called OH is coming. It can attack from this side, it can attack from this side. Right? Let's say primarily Br was here, but then now because of the formation of carbocation, Br has actually left and I got Br minus. Right? So the OH can attack from this side, it can attack from this side. Now we have learned about 2 terms called retention and inversion. Right? So if the OH comes in the same place as the Br where it was primarily was, we attain something called as retention. But if it comes from the back side, means from the opposite side where the nucleophile actually left, we obtain something called as inversion. Now since these two are symmetric, there is possibility of both in SN1 reaction. Hence, this is called something called as racemization. Yes. So, SN1 reactions are primarily occupied with something called as racemization because there is a possibility for both retention as well as inversion. Yes, sir. So, this is the example. So, we'll go to SN1 once more briefly. So, we have this compound alkyl halide, and the first step requires formation of carbocation. This is slow cleavage of the carbon and the halogen bond. Now, it breaks, we get a carbocation over here, and then we get an alkyl over here. After proceeding to that, we have an attack of nucleophile. That is the second step. When the nucleophile comes, we have something called as a trigonal plane structure. The one I have drawn there. So the nucleophile has two sides to attack. It can attack from this side, it can attack from this side. When it attacks from this side, we see that bromine was actually over here primarily. So if it attacks from this side, we're going to get the retentive product. Means there's not going to be any flipping of the product. We have H here, we have H here, right? But if the nucleophile attacks from the back side, which means bromine was here, but if it attacks from back side, we have something called as an inverted product. Means H was primarily here, but now it got flipped, H came this side, but OH is here. So these are the two, and the process called as racemization. Yes, moving on to SN2 reactions. SN2 we have learned it means nucleophilic substitution reaction bimolecular. So yeah, SN2 reactions are accompanied by something called as inversion. Just like in SN1 we have racemization, means both inversion and retention. But in SN2 we have something called as inversion. Means let's see to this example. We have a molecule, let's say this is a halide, let's say this is a carbon molecule. So let's say this is a nucleophile incoming. When the nucleophile is incoming, we see that the nucleophile, the leaving group is leaving from this side. But because of the steric factors over here, steric factor means it's basically a repulsion. Let's say there are two magnets, north pole this side, north pole this side. It's going to face a significant repulsion. That is the same happening over here. We have a molecule, we have a halogen leaving over here, which means that there will be significant repulsion from this side. Means the nucleophile can be only attacked from the back side, because when it tries to attack from front, there will be repulsion, so it cannot properly attack. So when it comes from the back side, we have something called as an inverted product, which means in the previous case, yes, we got an inverted product. H was this side, but then we actually got this side. So similarly, we have the three hydrogens, let's say hydrogens on this side, but after the product, we actually got hydrogens on the right hand side. And the nucleophile, which is actually supposed to attach on the right hand side, is actually got on the left hand side. So this is called as inversion of the product. Yeah. So I have developed a short trick to actually remember this SN2 reactions, which is, let's say we have an umbrella, right? We have an umbrella. Let's say it's curved this side. Okay, just like this. So let's say a strong wind is coming from this side. What's going to happen? It's going to get inverted, right? So in the same way, if there's a molecule in SN2 reactions and the nucleophile is coming from this side, the product is going to get inverted, right? Just like the umbrella's ribs, it's going to just get inverted like this. Means it's actually like this, but then it got inverted like this. Okay, so that's a short trick that I developed based upon SN2 reactions, which is the umbrella trick. Yeah, so you might be asking why only inversion in SN2 and why not retention just like the SN1 reactions. So yeah, let's say, so let's say there's a alkyl halide over here. We can say that there are three types of nucleophile that can attack, primary, secondary and tertiary. Let's say when the primary attacks, there's going to be a significant, not that much, but there's going to be a less steric hindrance. So if the nucleophile is coming from this side, it's going to face not that much, but a little bit less repulsion. But then we see that three bulky groups that are attacking, we can see that there is significant repulsion. So means the nucleophile has to definitely attack from the opposite side. It cannot go from the front side because it's going to face a repulsion. So that is why in SN2 reactions, we're going to want only inversion and not retention. But in SN1, we had inversion and retention both because there was no bulky group. Plus, this molecule is symmetric, means it can have two different sides to attack, right? So that's why SN1 is accompanied by racemization and SN2 is accompanied by inversion. So yes, this is a brief mind map that I've made. So yeah, stereochemistry and its applications, and we have learned seven different topics. First is chiral molecules, means the molecules which are four different substituents on each other. And next is achiral molecules like this one, which do not have all the four different, but then these two are same and these two are same. So this is achiral molecule. Next is SN1 reactions. It's a two-step process. Means the first step is formation of carbocation. Second step is attack of nucleophile. Yeah, and then the priority order is 3 degrees to 2 degrees to 1. That is because it is based upon carbocation stability. And since SN1 involves carbocation stability, this will be the order of SN1 reaction. And then it will be racemization due to its planar structure. Planar means this is called a planar structure, and due to symmetric site, it can have both inversion and retention. That's called atomization. And then in SN2, yeah, it's a single step process. It's just a fast attack. And then the reaction is going to be 1 degrees to 2 degrees to 3 degrees. That is because in 3 degree, we're going to have all the bulky groups. So we're going to face a significant repulsion. So it cannot attack from the original side. So it's going to attack from the opposite side. And it's also called as the backside attack. And then, yeah, so it's accompanied by inversion due to the steric tendons of the bulky groups. Yeah, that's it. So I would appreciate any questions.
What is D from and L from?
D from alpha, yeah. So as I've said, when the unpolarized light, it actually passes through nickel prism, it becomes planar polarized light. And these compounds, which are chiral compounds that we have learnt about, they can actually rotate this light in two different directions. It can go on the right hand side, it can go on the left hand side. When they go on the right hand side, we name it as dextro-rotatory. And these are actually called dextro-rotatory. And while writing angles, we usually denote by a plus sign. Okay, when it goes to the right hand side, we call it as a dextro-rotatory. When it goes to the left hand side, we call them levo-rotatory. And while writing angle, we denote by a negative sign. So a good way to remember this actually is, when it goes to the left hand side, it becomes levo-rotatory. So L, L. So that's just a good way to remember this. And if it goes to the opposite side, it's dextro-rotatory. So that's, I hope this question.
What is unpolarized light?
Huh?
What is unpolarized?
Unpolarized light is actually, see, when normal light sources are emitting light, there will be light that's going in all different directions. Means one can go in this plane, other can go in different plane, like there are many planes. So that is called as unpolarized light. So what we actually want is to rotate in a simple way. So we have used this prism that will rotate, that will make all different planes in just one plane. Yeah, it just combines. So it combines and makes them in one different plane, which were primarily chaotic before. Now it just makes it a simple one.
Can you explain chiral and achiral, like for example, each?
Yeah, okay, sure. Yeah. So let's say we have this molecule. We have a carbon, and it's different. It attaches to 4 different means chlorine, hydrogen, methane, and then an ethane. Alright. So chiral compounds means they have a chiral center in it, and chiral center is also sometimes called stereo center. Is actually when a carbon has 4 different molecules wrapped around it. That's called as a chiral center. So let's say we have a compound. We have chlorine, and then we have CH3. Yeah, we have CH3. So let's say in this compound we have this carbon. Let's name it. Now it has one substituent as chlorine, one as this, and one as CH3, and one as the other molecule. So since it has 4 different substituents, this is called as the chiral center of this molecule. And since this is a chiral center, this whole molecule is called as a chiral compound. Alright. So when we go to other example, we have this carbon. It is wrapped to Cl, Cl, hydrogen, and ethane. Now we see that these two are actually equal, and they are the same chlorine. So since it is not 4 different substances, we call it as an achiral center. And the compounds which have achiral center are called achiral compounds. Yeah.
What's the difference between enantiomers and diastereomers?
Let's say we have this compound. When it's rotated, these are non-superimposable compounds because we have this, and when it's flipped, we have other things. So when we actually mass them on top, they are not superimposable. These are called as enantiomers. Meaning, if let's say one has a plus, means it's dextro-rotated. It means the other should definitely be levo-rotated. Because if one rotates to right, other should definitely rotate to left. Now diastereomers, as per what I have researched, are the compounds which are technically not non-superimposable. Meaning just our hands. Let's say our hands, and then we have a plane of mirror passing like this. So if we have we're going to get a mirror image like this. So if we just place them like this, we're going to get a superimposed image. As per what I've studied, these are called as diastereomers. So when they're non-superimposable, they are called as enantiomers, and when superimposable, they are called as diastereomers. Any other question?
In SN1 reactions, which step determines the rate in the reaction?
See, actually the rate determining step is always called the slowest step of the reaction. So as we go to SN1, as when we go to SN1, so we know that the first step is the formation of carbocation, which is a slow cleavage of the carbon and the halide bond. So rate determining step, also called as RDS, is actually the slowest step of the reaction that determines the rate of the reaction. So this is a slow cleavage, it actually happens very slow in 2-step process. This is going to form a carbocation and the halide. So this is primarily the rate determining step of a SN1 reaction because it involves the slowest cleavage of the carbon and halogen bond. So since this is the slowest step, that will be the rate determining step of the reaction.
Why is SN1 faster in tertiary?
In tertiary, yeah. We know that the order is actually 3 degree is to 2 degree is to 1. So in SN1 reaction, it determines. SN1, it determines upon carbocation stability because it involves the formation of a carbocation, right? And for the carbocation, speaking of carbocation stability, 3 degree is always greater because let's say we have a deficient carbon, which is called carbocation. Let's say it has 3 different bulky groups. Alright, we have 3 bulky groups. So, since this is an electron deficient group, these 3 bulky groups are actually going to give electrons to this to make this more stable. So, the more the amount of bulky groups, the more electrons it's going to get, so the more stable it's going to get. This is actually determined by inductive and hyperconjugation effects, which we have learned last year. So that is why when there are 3 bulky groups, more electron rich, and if it is 2 different, little bit, and then if it's 1 degree, it will be a little bit less. So that is why, coming to your question, 3 degree is always more stable in the SMR reaction.